DevOps and machine learning is a very nascent and recent field, and it seems to be probably one of the key differentiators between companies who've been successful with their AI strategies and companies who haven't been. But before I dive into that, a little bit about myself and what I do. So I'm an engineer by training, but I've worked in multiple industries, including private equity, infrastructure, energy, fintech, and then most recently, I founded this startup called Dataspine, which essentially is an infrastructure agnostic, framework agnostic, machine learning operations platform that allows users to go from experimentation to production and post-production testing in a very seamless manner. And with that in mind, let's dive into what essentially is MLOps. I think a lot of this has been covered in the previous talk, but just to go over it once over, MLOps is machine learning operations, which is specialized DevOps for machine learning. It allows the different stakeholders in a machine learning strategy to collaborate and communicate better. And it also automates most of the grunt work associated with executing an AI strategy. The reason why this field itself has emerged is because there's a very unique thing that is happening with the current wave of AI that we are experiencing, in the sense that most of this technology wave is based around open source projects, and getting open source software to work in a way where you have multiple tool sets, multiple frameworks, multiple types of infrastructure, and then obviously getting it to scale, getting it to have a certain amount of uptime, giving your SLAs and such, that turns out to be a huge nightmare. And that's why this specific field has only recently emerged, where specialized operations platforms are being built to operationalize machine learning strategies. So as you know, it's pretty intuitive, but it seems to evade a lot of scrutiny, that machine learning becomes only valuable when you put it into production. If you build a great computer vision model, a great natural language processing model, a great natural language generation model, it doesn't really have any business value until you can put it into production and get it to do the task that you've trained it to do. However, that process of going from training and building a machine learning model to deploying and managing a machine learning model is very complicated, because the skill sets that are required for that process are very different from the skill set that is required for building machine learning models. Now, this disparity or sort of disjointedness of these two skill sets creates this chasm for companies between the amount of money and time that they're investing in machine learning and the return on their investment from that machine learning strategy. And this is exactly where machine learning operations slots in. It essentially bridges that gap that is created by these different types of skill sets, different tool sets that are being used in a machine learning strategy. Before we go deeper into the subject, let's just quickly look at what a traditional AI or machine learning development cycle looks like. So a data scientist starts looking at historical data, runs experiments to figure out, what kind of model they would want to build on top of that data, what will be the hyperparameters, what will be the features, and so on and so forth. Once they arrive at a suitable model, they then train that model on the historical data, test it on a holdback test data set, and then hand it over to engineering for deployment, or figure out a way to deploy it themselves. And once that model is in deployment, it is then managed in the form that it is monitored and evaluated in terms of the purpose that it was supposed to fulfill. And once the model falls out of spec, does not meet your threshold key performance indicators, you then go back to the experimentation phase or to the training phase, where you update the features, the hyperparameters, you change the data layer, maybe you change the framework that you wrote the model in, and basically build a new model and go through that same cycle over and over again. Now, the key thing to notice here is that machine learning software is very different from traditional software in the sense that it is not deterministic. While you can tell traditional software, while this is true, do that, or if this is false, then do this, machine learning software is probabilistic in nature, and therefore you must iterate upon it repeatedly until you get the desired level of business performance that you're looking for. Now, having clarity around the AI development life cycle, let's look at what exactly are the challenges or what sort of industry metrics there are around machine learning. So AI is definitely a very hard thing in the sense that while you have a lot of industry hype around the subject, globally, depending on who you talk to, anywhere between 70% to 85% of projects in companies fail when they are talking about AI. And on average, projects are taking more than 6 months to go from ideation to production and post-production. And despite all of this, in 2020 alone, about $50 billion were being spent on AI software. And if you were to use some very oversimplified math, you can potentially figure out that there's probably like $35 billion that are spent on AI software or AI projects are going to waste because 70% of these projects are failing. So that basically begs the question, why is it so hard? As I previously mentioned, there's a huge layer of complexity behind building AI projects because most of it is open source. Then you have data that companies are going to use to build their AI projects. These data sources are disparate, disjoint, reside in multiple locations. To give you a data point, we figured out that companies are using 5 to 12 different machine learning packages to develop solutions that are AI and machine learning focused. And over 80% of these companies are operating in a multi-cloud setup where they have compute, data, and other needs in multiple different infrastructure environments. Now, to add on to that, what we happen to have as a challenge is, as I said before, machine learning software is an iterative, or building machine learning software is an iterative process where you build, deploy, test, then go back again and again over to the same cycle. And unless you're able to do that very, very quickly and very effectively, you end up with projects that do not serve the purpose that they were supposed to solve. And therefore, companies declare their AI projects as failed projects. And this essentially is an infographic to show why this is so complex. You've got tons of different tools, you've got tons of different technologies, you've got different phases of the development life cycle, and all of this is residing on-prem, in the cloud, hybrid, private cloud, and so on and so forth. Now, getting all of this to work together in a single place is very hard, and in our experience, that has been the singular most defining characteristic of companies that have been able to leverage AI to build economic moats. So for example, some of the companies that have successfully used AI to their economic advantage would be Facebook, Google, Spotify, Netflix, Airbnb, Uber, etc. And what all of these companies have in common is that all of them have built in-house machine learning operations platform that basically allowed their engineers and data scientists to rapidly iterate on their machine learning models and test them very quickly, roll them out very quickly, and then go back to the drawing board at the same speed if need be. And just to give you some context at what the insane pace of iteration at some of these organizations is, so I'm sure you guys are familiar with Netflix and its recommended engine. So Netflix deploys its recommended engine or updates its recommended engine several thousand times a day. Amazon updates its model every 11.7 seconds. Etsy does it about 50 times a day. Now compare this to the 6-month lead time that we were talking about traditional organizations that are trying to adopt machine learning strategies within their business systems. So I think what the point that I'm trying to make is that in order to build a successful AI or machine learning strategy, an organization has to start thinking from day one about how they're going to handle machine learning operations, because machine learning operations seem to be the deciding criteria when it comes to a successful or a failed AI strategy. Now, having contextualized the problem, let's look at how do we actually solve for this. So a machine learning pipeline has several components. There's a data component, there's a feature component, there's the model layer itself, and then there's the evaluation layer. And the problem that typically happens is that data scientists work in an experimentation environment. They build a model, they pre-process data, they extract features, they build a model on top of it, and then they're able to get predictions from that model, and then they hand it over to engineering for deployment in whatever environment they're going to deploy it in. But that process of handover and change of environment produces unpredictable behavior from the machine learning model itself. And this is what I was referring to earlier as the crisis of reproducibility in machine learning, where the predictions from the experimentation environment do not match with predictions from the production environment. And that's because of multiple reasons. And this problem is very hard to solve unless you look at it cohesively as a singular problem, where you have something that addresses each layer of the machine learning pipeline. So starting with the data layer, you must have mechanisms in place which would allow you to version data, which would allow you to figure out timestamp data, to connect a particular time slice or slice of data to a particular model or a particular prediction. Then at the feature layer, you should have something that allows you to easily engineer features from your historical data, and not just engineer them, but allow you to store them and version them so that whenever you train subsequent models on those features, you can actually start tracing back your predictions and your bugs and any other provenance related issues that you might run into right back down to the feature layer. And then at the model layer itself, you should have a system that allows you to version models properly, allows you to have the appropriate transformations that are you going to apply to the input, output, or the prediction contract of the model, store them appropriately, and then have the same kind of environment both on the experimentation side and the prediction side, so that, the production side, so that when you actually put the model into production, you end up having predictions which are similar to the ones that you were getting on your historical data. And then most importantly, I think something that keeps getting ignored in a lot of places and a lot of companies that I've spoken with is that you need to invest heavily in your evaluation layer. So I'm sure some people would be familiar with the Mike Tyson quote that everybody has a plan until they get punched in the face. It's a similar kind of situation with machine learning models. No machine learning model survives its first contact with real life data. And whenever you deploy a model, you should be able to exactly monitor how that model is performing against live data, and how it's performing against the key performance indicators that you have defined. And these KPIs don't necessarily have to be technical in nature. They could be very business focused, or they could be proxies for business focused KPIs that you might want to measure. Now, having said all of that, let me tell you a little bit about what we do at Dataspine. So about three and a half years ago, I was heading this fintech startup that was building its own credit scoring platform. And within that credit scoring platform, we were supposed to put a lot of different machine learning models into production that were supposed to ingest data from different data sources. It was supposed to work on different types of infrastructure, so on-prem plus in the cloud. And it was supposed to give you predictions in the real time plus batch predictions. And what I discovered while managing that team was that building this kind of system or these kind of pipelines in the real world is extremely, extremely difficult. So I actually quit that job and went and built Dataspine, which essentially is, as I mentioned, a framework and technology agnostic platform that lets you handle the entire machine learning lifecycle through a single control plane, and takes you from experimentation to post-deployment management in a very seamless and intuitive manner. I'm going to skip some of the stuff, but just to give you, a sort of parting note, we know that machine learning is here to stay. It's going to be a generation-defining technology. But the important thing that we have learned after talking to more than 35 different data science teams at top-notch web-scale companies is that if you want your machine learning strategy or AI strategy to succeed, you have to invest heavily in machine learning operations, and you have to invest in it from day one.
Can
you give us a quick demo?
Yeah.
Absolutely. So this essentially is what the platform looks like. It's built on top of Kubernetes, so it's basically infrastructure agnostic. You can run it on-prem, in the private cloud, public cloud, or hybrid setup. And this demo is essentially going to walk you through a typical workflow for a data scientist. So a data scientist logs in, and the first thing that they do is that they provision a dev environment for themselves. And we've taken the route of notebooks. The data science community is kind of divided over this, but we can talk about the merits or demerits of it in another time. But in short, the data scientist comes in, names their notebook, picks up an environment that they want to work in. So we've got pre-configured environments which has frameworks and their dependencies and versions all controlled for. So they pick up whatever kind of workload they're going to be working on. The corresponding environment is chosen. The data scientist then allocates resources without talking to the underlying cloud. So X number of CPU cores, Y gigs of memory. It's create, that spins up a notebook instance. The only difference here with something like AWS SageMaker or Azure ML Studio is that we spin up our notebooks as pods, which ends up being much more cost efficient and faster than a traditional method of spinning up notebook instances and VMs. And this also helps notebooks scale when you're taking machine learning projects to production. And from here on, you're basically in a standard Jupyter Lab environment where we have a CLI tool that we wrote, so a command line interface tool with it that we wrote. And this is essentially that family of command line inputs that you can use to manage the workflow. And this is where essentially a data scientist would start their workflow. So they type in this command spinectl model init. It asks you for a couple of arguments which will control how the model goes to production. So what is the name of the model? What is the tag? So you can assign an arbitrary tag to do version control, and then later on track it in TensorBoard or our own model monitoring dashboard. Then you specify what type of model is. So what framework are you going to be writing in the model? And this controls a template directory, or what goes in that template directory that this command will generate. But I'll show that to you in a second. Then it also asks you for the runtime where you're going to deploy the model and what's the target chip. Once you do that, the command basically generates this template directory that contains files that you will need to take this model to production. So for the technically minded, there's a YAML file for dependencies and hard-coded variables. There's a prediction contract to define the input-output transform of the model. And then if you want to do training on this platform as well, then there's a trainer file there as well. What happens next is that assume that you already have a trained model and the output of the training run. So let's say you've got a TensorFlow training run and you've got an H5 file. You've imported it into this directory. So all you have to do is place the weights binary inside this directory. And what we do in the next step is automatically containerize this entire directory and take it to production. So spinectl model build manifest takes a couple of arguments, and what it does is it automatically generates a Docker manifest. So here's the Docker manifest. You then go to the next step, which is spinectl model build. And what this allows you to do is it allows you to push this entire directory as a container to whatever Git platform you're going to be using. So we support all Git platforms, and we can go into the specifics later maybe. And then you push, once the model gets pushed to the Git, it also gets pushed to our model repo. And it's going to show you that in a second. So this essentially is our model repo. Right. Yeah. So this is the model repo. This is where all the models that you have trained and want to deploy reside. And deploying this model as a secure, load-balanced, metrics integrated API is as simple as clicking deploy, typing in the name of the model. So for example, this is a credit card fraud detection model, and I want to deploy its 8th version. And I hit deploy, and now it's a load-balanced, metrics integrated API on your cluster, on your Kubernetes cluster, which we've built up. And you can fetch that endpoint from our CLI. But note that even though I deployed a certain version of the model, it did not ask me for the version. It only asked me for the name. The reason for this little quirk of the system is that we've actually built infrastructure level schema for users to programmatically define how much traffic they want to send to different variants of the same model. So if you've got 10 different variants of one model, we'll expose them behind this single ingress point. And behind this ingress point, we've got infrastructure that allows you to split traffic between different models. What that allows you to do is that it basically allows you to do testing in production. So things like A/B testing, multi-arm bandits, shadow mode deployment, differential testing. Traditional testing, which is done pre-deployment, we believe that's not a very robust and effective way to do machine learning operations, because real life data is what you want to be able to see your model's performance against. And once you do these kinds of splits, you can actually see the model's performance on our model monitoring dashboard, which is not here in the demo at the moment. But let me just quickly run through the rest of it so you can see how easy it is to set up A/B testing. So you just run this next command, which is spinectl predict create route. It asks you which model do you want to create traffic routes for, and then it specifies which model tag gets how much traffic. So right now I'm doing like a 50-50 split between V5 and V8. And in the next argument, it's going to ask me for shadow tags. So these are models that I want to put in shadow mode behind production models to test them before I actually roll them out to production. I'm not passing them anything at the moment, but now the traffic routes are created and I can load test my model. So I can give it some holdback test data file because I'm just doing an HTTP test, but you can expose it to live data as well. Asks me for how many concurrent requests do I need to send it. And there you go. The model is now live. It's supposed to output a confusion matrix where it is. And it's splitting traffic between the two variants that I asked it to split between.
Yang has asked, what are some of the major differences and hurdles you see between the more traditional statistical model-based MLOps versus deep learning-based MLOps?
Great question. So we've seen that it's basically the traditional statistical machine learning versus deep learning. At the end of the day, if you've built the pipeline robustly, it should function reasonably well. However, it's been in our experience that deep learning focused models tend to require lower latencies just because of the use cases they're in. And you must configure your infrastructure accordingly depending on what kind of latency you're looking at. So what's the second part of your question? In your experience, do most companies roll their own model monitoring solution to use? Oh, so monitoring is interestingly something that even very mature companies have ignored to date. Even some of the more robust solutions coming out of AWS, Azure ML Studio, GCP AI Lab don't have intuitive testing and monitoring frameworks built in. So people are either doing ad hoc monitoring or they're going specific third-party vendors that have monitoring solutions available. That's exactly the reason why we've built an we have an inbuilt model monitoring dashboard that allows you to measure model KPIs, business KPIs, but we've also configured it to measure data drift so that once your production data has deviated significantly from your training data set, the data scientist should be alerted by saying that your model is basically throwing junk now. Go back to the training board and train the model again with new features and new data.